on some of the ideas, which I want to definitely emphasize. So I'll go right on, hopefully I get the right buttons here. There we go. So what I'm really after is to show through visualization, what I'm after here is, I'd like to define a macro applicability to quantum theory. And I think this is sort of the next wave, is, you know, we want to try to get quantum theory to apply to something other than the microcosm or the very distant macrocosm. And I want to accomplish this by visualizations, specifically visualizations of the Hilbert space. And in order, and what I'm after is to follow the concept that Heisenberg, as well as Bohr and other people kind of thought about, which is that quantum mechanics is actually the physics of the system that knows the world. That's us, right? So let's go on. Here's the cartoon system that kind of knows the world. On top here, I'll explain this a little later, but if you happen to know this, this is Mach's view of the first person. You can see his nose here. So if you want to follow that, close one eye, and this specific thing, close your right eye, find your nose, put your nose here. We're talking about the first person point of view. It's the only view you have,
right.
And it's everything that you ever know, and all your theories are always derived from that kind of view, first person kind of view. So that's kind of important. But notice, in here, I've drawn an apple, because I happen to like apples, and it represents an observation, so a sensation. Okay? What happens? What does the first person do? You take an observation and you try to find an explanation. What's the explanation? You see something, most likely your explanation is going to be that, well, some stimulation hit my sensors. Now, what I've drawn here is an internal view of an independent person. I'll talk about interactions later. So this represents the system that knows the world that happens to be dreaming, which we all like to do. All right, so what's the next thing? You explain it. You explain, you say, well, something hit my sensors from an outside world. Okay. Once you find the cause presented to yourself, in yourself, right? Then the next thing is, well, okay, I'm going to measure that cause, and I'm going to reproduce the sensation. And what you find is that this is what we do.
Science, yeah.
You know, we people, not science. Well, science too. In fact, I'm glad he introduced the next slide. So I'm just saying, this is what we do.
Yeah.
But it's not only us as persons. You know, I'm not a soft-headed guy. You know, it's not just us. It is science. So here is. This goes pretty fast, doesn't it? So here is quantum mechanics. All right. This slide was inspired by Henry Sapp. Actually, he said that there actually are the two processes, von Neumann's process 2, von Neumann's process 1 as the measurement process, and he introduced the process 0 and the process 3. So essentially what I'm doing here is I'm saying, look, the quantum mechanics is actually a documentation of the physicist's thinking process. Right? And what does it look like? Over here, these are measured observable. This is everything that you can possibly see, right? Experience. And what is it? What is it? It's energy times time. So this means the action hits. Photons, whatever else, they hit you. That's the stimulation. You explain it by the explanation is in quantum mechanics, not in classical mechanics, but in quantum mechanics is that energy times time goes into a wave function. Right? The wave function is somehow stimulated in your sensors. There's a unitary transformation that transforms it to some other time. That time now is measured, and you reestablish the observables. So you're constantly doing that. And that's, in fact, what we scientists are constantly doing, except instead of being internal, it isn't externalized. We've tried to do this entire cycle has been externalized, and you can see it individually in papers. But if you look real carefully, there's always a physicist involved moving that process around. So to show you how, see there's the action, there it is, there it goes in the wave function, there's the wave function, that gets transformed through your unitary transformation into the wave functions over here, where it produces the action again. Okay, so what I've got here is an action cycle. If you look at the top, this part, this is a drawing, of course. Everything I'm doing here is just a drawing, a representation, you know. So the top part is the part that flows through you directly. This is what you see. What you see out there is action hits on your sensors interpreted. Right? So these are action hits. That's the part that flows through you. You can see, you know, this is what I tried to do is show a cycle, but show the different aspects of it, and so you can kind of see one thing. The only way you can see this part is to be the cycle itself. You've got to be in it. The bottom part, which represented the explanation, this is where the action flows past you. Okay, so you've got two aspects. One is what you see, action flowing through. The other is how you explain it. You explain what you see as though you were looking at it from the outside. So inside and outside are fairly important concepts here. All right, so did I get to, or is that? Okay, so now I'm going to talk about the reality illusion. And I think that one of the important things is that we physicists tend to believe we're dealing with reality. And we poo-poo other people who have other ideas about, you know, so on and so forth, about the subjective things, and we try to get rid of those people. And what we don't realize is how subjective we are ourselves.
Yeah.
Okay. Well, you take a look at that. The reality illusion problem is, how can we ever know the real physical explanation? You see, here's what we've done. We've taken sensory hits, we explain them into a theory. The question is, how do we ever know the real physical explanation offered by any theory is correct? So we got this theory. How do we know it's right? You can't see it. You can't see it. All you can do is measure something and then compare the measurements. Right? So this is a theory.
But even then, the physicist doesn't know whether the apple is real or a hologram.
Correct. Exactly.
Right?
Right. So all we can do is compare things at the observational level, and then we theorize about it. You know? But now, how do we know the theory's right?
Could be dead wrong.
Could be dead wrong, yeah.
Be dead.
That's the good one.
You know, dead's a good word, actually. If you're wrong, it might be, you know. So the answer is we cannot know, you know. But, you know, here's one thing. All we can do is make symbols that work. Okay? We don't know what the reality and the cause of our sensations are. But we make symbols of them, and we operate with those symbols. So let me go on and how that works. So here's an example. Right? Now, this is a calcium ion. You know, it's from the Los Alamos Paul trap. Okay, so now I've already made a mistake, because what have I just done? I've said here is a calcium ion. Right? So and you probably haven't noticed yet, but that's a mistake, because it's not. This is not a calcium ion, right?
No, but we are polite.
It's light, right? So exactly, you know. So what do? We have to now explain the light. So here we go. Here's the famous Mach drawing, which I, by the way, adopted my thesis back when I got my PhD in Berkeley. So here, what we actually see is light. What we do is attempt to explain it, okay? And this is a cartoon drawing, so one way to explain it is to say, well, let's visualize a Bohr atom. So now we visualize there's a plus charge, there's an electron in one orbit, and the explanation is, well, the electron, this is a visualization of the explanation, is that the electron must have dropped from one orbit to another, a photon comes out, and it produces the light. So that's kind of where you get both your actual sensation, and now this is a sensation of the explanation. Okay? The next thing we do is we project the visualization of the explanation back into the sensation. Okay? So I see you, but what I see is just, sort of a blob. I'm sorry, but sort of a blob, right? But my brain instantly says, well, there's a person, so on, and a lot of stuff. And the sensations that represent that reality is immediately projected in. I think I'm dealing with a real person. I probably am dealing with a real person.
Probably. But, how much doubt do you have?
Well, we'll go on with that. Let's not explore that one too much. All right, so, but what we're doing here is adopting what I call the reality illusion. And this is what Bohr warned us against, which is don't take the visualizations of your symbols seriously. Okay. Here's the actual mechanism. Okay, this is probably the most important slide I have to give. All right, so there's two things that happen. Here's the light. Here's the explanation. Here it goes to the simulated sensors internally to our theory, all symbols here. And it goes around and measure it, and I reproduce the light, or I reproduce the expectation of the light. That's how I operate. When that works fine, everything is nice. I walk around, I turn my head. There's a lot of stuff going on, but when I turn my head, part of me turns the other way so that everything kind of lines up, right? But the explanation now, right here, this happens in a different modality. Okay? The sensation came in at the optic modality. The explanation is presented to you in your imagination modality. And what is that? That's the one when you close your eyes. Just try it. Close your eyes. You have all kinds of sensations. I know where the walls are. In fact, I know where most of you are. I just close my eyes. I know where you are. That knowledge is a sensation. That sensation comes to us through an internal second cycle of activity. Okay? So in one case, you're seeing something from the front. In the other case, you have imagined an explanation here. And now see these thought bubbles is the typical mistake that we make, which is that the thing is explained by our visualization of the explanation, when in actuality, the only way we can deal with it is to say, we operate on these symbols. Now, what's a symbol? A symbol has always got two characteristics. One characteristic, a symbol has a meaning. In this case, the meaning is this. That U represents something out there that is our imagination of the universe. It also has another. All symbols have some physical implementation. As a physical entity, it is a physical operator. This represents, in the physicist's brain, this represents tangible structures in the physicist's brain that is doing operations on the sensations that are coming in, that are being processed around it, that cycle. Okay, so, symbols have two sides to them. The symbolic side and the actual mechanical side. Every piece of thing that you write down on your piece of paper has a symbolic significance, and it actually is a physical thing that does physical stuff to other symbols in your symbol system. And the best thing is to look at a computer system when you're a programmer, right? The symbol has a meaning to you as the programmer. You put it in a machine. The machine doesn't know anything about the meaning. It becomes the physical entity that processes other systems, including your input, and then gets you an output. So all it is too. So that's what happens. So So now I project the explanation, which now is a symbolic, back into the light, and I say that, as Bohr says, you know, we're only going to project back the symbols back into the, we're not going to project the visualization of it, and then shut up and calculate. So this is basically Bohr's suggestion to us physicists. So now, if we believe that there are really probabilities whirling around, you know, we're still doing what Bohr warned us against. We're adopting a quantum reality illusion. There may or may not be, it may or may not be useful, but certainly if we take the symbols of quantum mechanics and interpret them in terms of probabilities, we are adopting some, and then adopt those visualizations of probabilities as clouds of probability. We're doing what Bohr said not to do, you know, which is we're visualizing something, and he says just deal with the symbols. If they work out, that's all you need to do. Now, why do we need to accept a reality illusion? And the reason is that we're simply built only to have, at this stage of our evolutionary process, we're simply outfitted and built with a three-dimensional visualization capability. If we don't project something into this space that we see in front of ourselves, got it.
20 people.
Yeah, you're 20 minutes. Okay. There are a lot of ways. I know it's very difficult for most of you probably, well, some of you maybe not, but it's going to be very difficult for you to recognize the fact that everything that you see in front of you is an internal construction of the larger mechanism that you are. To make yourself aware of that, there's all kinds of ways of doing it. Okay? I'm patenting some devices. And the simplest device is called binocular rivaling. If you take a couple of mirrors and you put them up so that you split the input to your brain from the left and the right side, what your brain will do is will choose one of those inputs and it will produce a three-dimensional view in front of you that is as real as you see right now with two of them. And after about 20 seconds, the other one will come in, and that will become as real. Your brain is generating the thing that you see in front of you as the result of a process that hits your eyes. It's not just out there. It's the result of the process. And that is how the observer is in the quantum system. It's because the things that he sees, the observables, are part of his own processing cycle. Okay? It's not a separate thing. Now, it's hard to live like that. You know, I certainly don't drive my car thinking this is all internal, you know. But when we're starting to analyze the theory that we're involved with, we have to start keeping that in mind. So the next thing is I'm going to project this image of the Hilbert space. And now what is it? Now, knowing full well that this is a projection, I'm going to say, okay, Hilbert space is in fact the tangible physical detector cells that we do our measurements with. It's not an abstract space. It is, the abstract space comes from the fact that we have tangible things that make the measurements, and they can be visualized in front of us. So inside here says, let's take a look at that a little bit. So the hypothesis is that Hilbert space, and this is not anything really new, but the Hilbert space, or the mathematical part of the Hilbert space, is simply a description of tangible physical detectors, or arrays of detectors that represent our retina or extensions of it through all the instruments that we have, which are really just extensions of our own personal measurement. Okay, so now let's take a look at the Hilbert space a little bit. So what this means for physicists is that the real world is out here. This is a cartoon version, of course. Electromagnetic stimulation and gravitational stimulation hits our detector cells, and we, conscious beings, are looking at the inside of them. Right? So there's an inside and an outside. So we, conscious beings, when I'm seeing something, I'm seeing the inside of my detector cells. Okay? So here I am, this conscious being, looking at the inside. I've turned them around now. So electrogravitational stimulation hits the real detector cells. I see them, I get the sensation of my apple, and out here goes the future. So this is the past future, so this is the action flowing through, represented in a linear fashion because the closing of the circle is a fairly large one. So this is our second person point of view. And now Hilbert space defines a field of classical systems. Now comes the next stage. I have reduced all the complexity, and I'm not saying that it's great. I'm just saying that everything that I've seen here, especially the tremendously excellent presentations we've heard, are in my just temporarily summarized with something simple. And what I'm saying is, which I love the fact is it's mass charge, is that I'm going to say that, you know, I've got a cell, or I break up my detector space into individual cells. They're made out of classic physical systems. The classical physical systems have mass and charge density in the space. Time is the flow of this action through the system. So this is a snapshot. And for simplicity, I'm going to say each one of those cells, I'm going to describe this whole thing for, again, simplicity, a charge and a mass center. And I think yesterday I said, you know, those aren't actually real, so behind the thing are the densities. But in order to handle them, we usually have to break them down into the centers of mass and the centers of charge. All right, so our Hilbert space is now made up of all of these individual cells, each one of which is at a primitive level characterized by a charge and a mass center. The charge and mass centers represent a distance. That distance, the charge-mass distance, can be summed up to become the whole space. And this is my postulate in the sense that charge and mass in the past have been usually considered to be located in the same spot. And I'm suggesting that charge and mass have to be held together by something, and that something introduces forces that mass and charge attract each other, or maybe repel each other, but there's a force between them, and that force is something that you're not going to see from the outside, so it's a postulated force. So a cell in one of the detector arrays will be characterized by electric forces pulling the electrical part in one direction, gravitational forces pulling it in the other direction, and the two forces between the two combining the two so that you end up with having forces on the charge and mass, and if you add them all up, you end up with an extended D'Alembert principle, which is basically an extended version of Newton's second law that includes gravitational forces, past and future, electromagnetic forces, past and future, and these forces that hold charge and mass together. Now, what does that do? Probably do. So I'll just go through this real quick, which is, all right, here's the apple, any system around. Break it apart like we usually do. Make it as small as possible. You break it into two pieces. all you see is gravitational electromagnetic forces between them. Break it apart some more, still electromagnetic forces between them. Keep breaking it apart, all we ever see is the outside of things. Science always looks at the outside of things. And the outside of things has gravitational long-range forces and electromagnetic long-range forces. I'm postulating that for simplicity, and I'm not saying that all the wonderful work that gets done in the high energy field is wrong. I'm just saying that for our purposes, we might short circuit some of that stuff and just say that charge and mass have to be held together by something. So internal, I'm postulating that there are these forces holding charge and mass together, which you can't see no matter how small you break the stuff, because we're always looking at it from the outside. In order to feel the internal forces, you have to be the cycle. You have to, that cycle has to be you, and that is in fact what I'm postulating. That the bigger mechanism of yourself, of your cognitive being, is a cognitive action cycle, which modifies its own self to accommodate forces from the outside in its internal structure, and that internal structure is in effect a balance to the outside forces. Now there's a book written by Giuseppe Vitiello. He's you've heard of him, right? And it's called The Double Inside. And what he's done is he took the brain and he said, you know, the brain, he wanted to find a cognitive mechanism. He said the brain can't be analyzed in normal quantum mechanical system because it's an open system. And he said, I've got to double the degrees of freedom. So he analyzed the brain as a doubling of degrees of freedom, where one set of degrees of freedom represents the internal accommodation to the outside, meaning the internal model that you hold. And so that's essentially what I've done, except I've said, well, instead of doubling the degrees of freedom and still keeping charge mass the same, I'm going to give charge one set of degrees of freedom and mass the other degree, put a force in between. And what that does is allows me now to look at the quantum approximation, which is when the charge mass is separated by very small amounts, you can represent the attraction between them by a spring, meaning linear, and then you can calculate out, in fact, this can be done classically, and there's a great chapter in, I don't know if you know Goldstein's Classical Mechanics. It's probably one of the best books ever written. And chapter 10 is a calculation that shows you how to take small, it's a chapter on small oscillations, and it shows, not exactly, but one can use the equations in there to show how the Schrödinger equation can be derived by assuming an array of cells in which the charge and mass, or two systems, are held together by small springs, and interactions between neighboring ones will produce small perturbations, and the motion inside these arrays of cells can follow Schrödinger's equation. In other words, they oscillate. All right, so, okay, so now I've projected, I'm hitting the right thing, I've projected this thing that we see. Well, you see it from the outside. Inside here is our quantum mechanical operators implemented by connecting the charge mass separation field interpreted from quantum mechanics as Schrödinger's wave function by the U operator into the future one, and then it goes back out and radiates into the future. If we turn it around, this is now a typical object of any kind, and you can see that what's inside here is completely hidden. You can't see it. That corresponds to everything you see, including the second person. You have no idea how you think about things or what you feel, and it's totally hidden. I don't care how often I chop you apart, I'm never going to find it. I can't chop a second person's brain apart and find that internal structure.
Oh,
I have to be the structure, and then what I see is the internal structure because I am the cycle.
So
but if I look at it from the outside, I'm looking at a second person, it's always hidden inside.
So why can't you say or deduce that my structure is similar to yours?
Yeah, that's what I'm saying.
Doing that, okay.
But my personal first-person experience is I'm looking at the backside of my sensor arrays, the output of my sensor arrays. When I look at you, I'm looking from the outside, and I'm not going to see what you see. So it's always hidden. All right, so let me just go on a little bit. These are some calculations as to how to do this. In order to actually get the calculations, I usually have to assume that there's a force in the back that would like the charge to be in one place. From the future, the charge would be the other, and internally there are forces holding them together. So then I get some equations, and down here I end up with two coupled equations. One saying that the force on the mass and the force on the charge, and the sum of those always have to be zero because material only happens where all the forces on it are zero. That's the fundamental statement in physics. So I'm going to go through these, but this is ways of doing some calculations on it. The next thing, I got 5 minutes, I think, is does this mean for the macro applicability of quantum theory? Does quantum theory apply to atomic and nuclear phenomena because of the small size, or because h is not zero? And the answer, in my answer at least, is no. Quantum theory applies because the explanation of the cause of the observable can in principle not be observed. It doesn't, there is always a non-observable explanation to what we see. Religions do it. If you were a Greek, Athena would be there behind me, with a big spear, right? That's the explanation. We project that in. It doesn't happen out there. It's something that happens on the inside. And the same theory, the same cycle, the same concept that you explain sensations through a model of yourself and then back out again. And what that implies is that what physicists have not done is recognize that we can divide the flow in time into an objective, meaning that's where electricity and magnetism comes in, subjective, whatever is the inside of material, which I've simplified by saying it's charge-mass interaction, then objective, subjective, objective, subjective, and physics, because it only looks at things from the outside, has simply collapsed the subjective into the interior and then made up many wonderful experiments to find out, the details of it. Many of those experiments are simply, if you guys have ever known of Eddington's fish story, but essentially what it says is that if we dig deep enough into the universe, we're going to find the construction rules of the system that knows the universe. In other words, the more we learn about that thing out there, what we're really doing is finding out more about our own construction, of our own investigation. And I think if you actually think about what CERN is doing, you'll see that a lot of what they're doing is finding the rules of their own system of investigation. So it's not that they're wrong, but maybe they're barking up the wrong tree, the wrong methods. I'm out of time, but the next thing I was planning to do real quickly is to say, well, let's apply some of these ideas to macroscopic problems. Here is a simple example. An apple is an apogee. It's at 0. It's got some, it's got some position. It's got some momentum. Momentum is 0 because it's standing still at apogee. It's got some position, right?
Yeah.
Now, if I take that and put something right underneath it real fast, versus thought experiment, I'm going to find the same position. I'm going to find the same momentum, but it's pretty clear that the left and right side are very different. Okay? This cannot be explained by the Newtonian approximation of charge and mass being at the same point. But it's what we always do when we talk about elementary particles, right? Or most of the time. So in actuality, the bottom here pushes up the charges. Now, of course, I'm projecting what's going on here at the bottom of the apple into its center. But the charge is pushed up. There's a slight difference. And in fact, there's a small difference in position between the charge and mass. And it's that force, the gravitational force, pulls the charge down. The force from the table pushes the electrical up, and it's being balanced by this stuff in between. So that's an example. Here's another one. This I haven't totally worked out, but it's possible to take a Bohr orbit and say, well, wait a minute, if the electron's moving around, there's a slight change. The electron is being pulled in, the charge part. The mass is pulled out by centripetal forces. And so there's a slight difference between the orbits of the mass and the orbits of the charge, which should produce a very small change in the orbital radius and the frequencies. Haven't fully connected that with the fine structure constant or some kind of fine structure, but I believe I'm working on it. Here's another example. This one comes from Penrose's, and Penrose's OR, orchestrated reduction. The idea here is that an influence comes in, it moves the charge a little bit. The mass would like to follow because it's being attracted. So it has to tell the rest of the universe that it's going to move, it's an electromagnetic, a gravitational thing. The rest of the universe has to come back and say, yeah, it's either okay or it's not okay to move, because it may not have a place for it to go. And so based on the return of the gravitational signal, the incoming photon, for example, bounced off of a mirror in a Mach-Zehnder, 1 minute, okay. So in other words, the indeterminacy of our quantum states does, like Penrose suggests, depend on a gravitational interaction. And as a result, either the photon is absorbed, like in this case, and the mass can go back to where it's charged, or it's not, in which case the photon is rejected. And in most of we can have experiments, and that's why sometimes a photon will go in one direction, and sometimes it will go in the other direction. But at least according to Penrose, and I think this is a good explanation of it, because there is a gravitational interaction. That's the summary. I won't read it, you can read it yourself. But the summary of the theory is fairly straightforward, which is that the full universe as we know it is actually representable by an action cycle that is moving, in other words, a flowing action, probably at the speed of light, but I'd rather say the speed of now rather than the speed of light. I think the constant should be the speed of now. The speed of light changes an awful lot all over the place, so the speed of now, and we've heard that it might change in the gravitational field, so I'd rather say it's now. We are one of these cycles, and we interact with a lot of other ones. I'll move that along. So this is a picture of a universe of interacting cognitive action cycles. But before I finally go, I do have to say these are some advertisements. Maybe I haven't. I've got, this stuff has been described in, these publications. This one you can get on the internet. The other ones cost money. This one is the best one. You can get it on the internet, and it describes this force of consciousness and the mass charge interactions, and how by adding a force between mass and charge, we can get the subjective into the standard, not standard, but slightly expanded physics. Okay.
Thank you. I think we go straight to coffee now. We've run out.